So we ask the question, what's the net force on the car? Well, the weight vector can be replaced by the Wy and Wx vectors, so we draw the wiggly line through the W vector to indicate that it's been replaced by the Wy and Wx vectors. We know that the cart moves along the incline because the incline is strong enough to resist the Wy force that's pushing the car into it with an elastic or compressive restoring force in the opposite direction. So the car, again, is being pushed into the incline by the Y component of the weight force. The incline pushes back with an equal and opposite force. And we call that, I'm going to use F sub n for the normal force. Matter of fact, I'll even write out the word normal. But usually we'll just write F sub n for the normal force. I didn't draw that vector quite long enough. You can correct that. You should be kind of sketching these things as you go anyway, because that helps you get it into your brain. So, and of course, many of you have already had a statics course, and you've already pretty much got this into your brain. So, still, try to get the flavor of what I'm telling you here. Okay, so you have that normal force. Now, this is a picture that includes the incline, the horizontal line, the car. Just want to break this into or reduce this to a free body diagram where all we've got is the x-axis, the y-axis, which we have here. Here's the x-axis, here's the y-axis. But then I'll draw the normal force, and I'll try to draw that just a little more accurately. And here I'm just going to write that as F sub n. Now that's the normal force, assuming that there are no other forces acting on this car perpendicular to the incline. For example, now I could be pushing on this car with my finger. I could be pushing it in this direction. That push would have an x component and a y component. The x component of that push would tend to accelerate the car up the incline. Might or might not be successful in doing so because the Wx force is going to be tending to accelerate it down the incline. So that would all depend on whether the x component of my force was greater than the Wx or not. There could also be frictional forces, so we'd have to take all that into consideration. But the main point is the effect of a push here on the normal force. The y component of that push tends to push the car, excuse me, allergy season, into the incline. So the normal force would have to be even greater because you'd have the y component of the weight pushing the car into the incline. You'd have the y component of my pushing into the incline. That would increase the normal force. The condition here is going to simply be that the net y force equals 0. So the normal force is, assuming the incline is strong enough to withstand it all, the normal force is going to be equal and opposite to the sum of all other forces in the y direction. In this case, we assume that nobody's pushing it into the incline. The only force in the y direction is going to be the y component of the weight vector. So over here, we'll put our wiggly line through the weight vector to indicate that it's not really part of this. It's been replaced by the Wy and the Wx. We got our normal vector, our normal force vector, that's equal and opposite to the Wy vector. It looks like I made it a little bit short again. Again, you can correct that. You should practice doing that, making good, accurate diagrams. So what happens? This force has been replaced by these two. This force is equal and opposite to this force, so they add up to 0. All you're left with is the Wx force. That's the net force that's acting on the cart on the incline, and that's the force that will accelerate the cart down the incline if we happen to be working in the absence of friction. However, as we can easily see from the situations that we've set up, there is going to be some sort of a frictional force. So that, using a slightly different color of chalk here so that you might be able to see it. Okay? That's going to be the force of friction. And I'll designate that. A lot of times that's indicated by lowercase f, but I'm going to indicate it by a capital F with the FRICT abbreviation of friction. So now we have that frictional force, and we're going to have to add that frictional force to our diagram. Here it is. And we'll have to add that frictional force into this diagram. And now, we can draw our final diagram, and I apologize for blocking it, but you'll see in a second. Okay, there's another set of x and y axes, and we simply add these two forces. Okay, now I can kind of isolate these forces. We got the Wx, and we got the negative force of friction. Well, the force of friction, which is in the direction opposite. And if we put these vectors head to tail, this vector plus this vector equals a shorter vector in this direction. So that our net force will be reduced. Now, that assumes that the force of friction is in the direction up the incline, which it would be if the cart happens to be moving down the incline. Now, the cart could have been given some initial velocity up the incline. So if it's moving up the incline, the frictional force is going to turn around and reinforce the weight force. And I believe you've had a problem that deals with that in some sense. In any case, the force we get then is F net. And if you can draw this picture more or less accurately for a given situation, the calculations become very simple. Now we'll move on and do some calculations. We'll write out the results in a minute. But again, my point here is you should be able to picture this whole process. The picture guides your calculation, helps prevent errors, and just gives you a much better understanding of what's going on. So, always draw these pictures. Use the pictures to make sense of the situation before you do any calculations.